welcome to the next class. Today we are going to talk about another distribution that is called Poisson distribution. In the previous class we talked about the binomial distribution. In binomial distribution you have n samples and you have k successes and probability of each of the successes is half. So you are expected to find out the total probability. Whereas in Poisson distribution, when n becomes very large, then the binomial sort of tends into Poisson distribution, and that is what it is all about actually. So we have the probability of a number of independent events occurring in a fixed time. Okay. So the probability of a particular event occurring in a fixed time. For example, number of car accidents that is happening in a metro city in India in the past 1 month, or number of infant deaths in India in the past 1 year, and so on. So we are talking about based on a large number of data, we are trying to find out the events actually. So the probability p will be very small, whereas the number of observation will be very large. So it is sort of related to the previous one which we saw, the binomial, but here the n is very large and p becomes very small actually. So this is also very useful in biology, as I am going to talk about a few examples. So the Poisson distribution, the equation looks like this: e power minus lambda raised to the power x divided by x factorial. Okay, x could be 0, 1, 2 and so on. So how do you know lambda? Lambda is given by this relation n into p is equal to lambda. So here n is very large actually. So some events are rather rare, they do not happen often, like car accidents or infant deaths and so on actually. So for example, number of mutations in a given stretch of DNA after it is exposed to radiation. So in such sort of situations we use Poisson distribution. Okay. So the equation is like this: e power minus lambda x divided by x factorial. The lambda is given by this relation, n is the total data set, p is the probability of occurrence. So x could be 0 if you are looking at 0 event, x could be 1 if you are looking at 1 event, 2, 3 and so on actually. Okay. So let us look at an example. Suppose the average number of fatalities due to car accident in a city in India on any day is 5. So this number one might have collected over a very long period of time. Okay. So it is almost like a huge population data, and then you get this data actually. Okay. So it says on any particular day there could be 5 accidents which lead to a fatal result. So what is the probability that fewer than 4 such fatalities will occur on any particular day? So if I say tomorrow, what will be the probability that fewer than 4? That means it could be 0 accident, it could be 1 accident, it could be 2 accident, it could be 3 accident, because you are saying fewer than 4. So what is the probability, say if tomorrow in that particular city you have fewer than 4 accidents? So what do? You know this equation, e power minus lambda x by x factorial. Okay, and you need to put x is equal to 0, then x is equal to 1, x is equal to 2, x is equal to 3, then add up all of them. Okay. So what will be the lambda here? Lambda is 5, because we are talking about in any given day, and statistically they have found that there will be 5 accidents per day. So lambda will be equal to 5. Okay, then x you put it as 0, then x you put it as 1, you put x is 2, then x is 3, then add up all that will give you the entire probability. So the probability that fewer than 4 accidents take place, that means x less than 4, that means it can be x0 or x1, x2, x3, and lambda is 5. So what do? E power minus lambda into lambda raised to the power x, in this case 0 divided by 0 factorial, then e power minus 5 raised to the power 1 divided by 1 factorial, e power minus 5 raised to the power 2 divided by 2 factorial, e power minus 5 raised to the power 3 factorial. So 0 factorial is 1, and anything raised to the power 0 is also 1. So when you do all these adding up, you get 0.265. So the probability of having fewer than 4 accidents, say tomorrow or any particular day, will be 26.5%. that is what it is. Okay. So we can also check with the online software. Yesterday I introduced this software called graphpad online software. and this is the link for that software. We can do the same calculations with that software also. Okay. So I can substitute and you get 0, 1, 2, 3, 4. So if you do the cumulative, as you can see, for 0, then 1 cumulative will be this plus this giving this, for 2 cumulative this plus this plus this, for 3 cumulative this plus this plus this plus this, that comes to 26.5%, which is matching with 26.5. Okay. So let us use the graphpad. Okay. So let us use the graphpad software. So as you can see, it tells you that we can use binomial, Poisson and so on. So we use this, then go forward. Okay. Then this is the one, we again use this and go forward. So we have here it says Poisson distribution. So average number of objects, that means on an average they have seen 5 fatalities on any particular day in that city. Okay. So we put 5 and then we calculate the probability. So you see this, so for 0 accidents on any particular day, the probability will be 0.67%. For only 1 accident, the probability will be 3.36%, but if it is 0 or 1 accident, then you need to add these two, that is cumulative, so it comes to 4%. So for 2 accidents it will be 8.42%, for 3 accidents it will be 14%, but if you are talking about 0 or 1 or 2 or 3 accidents on any particular day, you need to add all these, so that is the cumulative, so we get 26.5. Okay. So we got the same answer. So we can use this graphpad software also to do the same calculations. Okay. So and that is what we got here, 26.5% for less than, fewer than 4 or less than 4 accidents. Okay. Okay. Even Excel has this option. We have something called function called Poisson. X mean cumulative, X is the number of events. Okay. X is the number of events, M is the mean, that means M is the expected numerical value, cumulative, true or false, like in binomial, if you put false you will get the exact value, whereas if it is true you will get the cumulative value. So we put total as 5 and we want to see, look at 0, 1, 2, 3, 4. Okay. So we can use the same function here in Excel also. Let me do that. Okay, we go to the Excel. So we say equal to, okay, data, yeah, sorry, formula. So we have the statistical, then we have the Poisson. So you see the Poisson distribution. So when we say Poisson distribution, X is the number of events, okay, mean is the expected numerical value, okay, and here we put false to get the absolute, or we can put true to get the cumulative. So X is the number of events, 5 for example, I want to look at say 3 and then I say true, okay, and then I get this. Okay, so it gives you something here, okay, which is not correct. Okay, so you got 26%. Okay, so so in the Poisson distribution we have X is the number of events we are looking at, mean is the expected numerical value, okay, and the cumulative is true in this case. So here we are having 5 fatalities expected on any particular day, but we are looking at a minimum of less than 4. So I have put 3 here and I have put true here, and we get the answer as 26.5. Okay, so which matches with the whatever, okay, for whatever we got here. Okay, we got 26.5 and 26.5 using different methods. So, we can use this formula, or we can use this graphpad software, or we can use this Poisson distribution function that is available in Excel as well actually. Okay, here, so we say x is the number of events we are looking at. Okay, so it could be 1, 2, 3, 0, and then this is total. Okay, and then cumulative could be true or false. Okay, let us look at another problem where Poisson distribution is useful. The probability of a birth defect is 10%. This is data which is maybe collected over a very long period of time. Okay, so the probability of a birth defect is 10%. So, what is the probability that no one in a family of 10 people have the birth defect? So, I have a family in a village, there are 10 people. What is the probability that no one in that family will have this birth defect? But the probability of birth defect is 10%. So, how do you do this? Again we need to know lambda here. NP is equal to lambda. Okay, here n is 10 people and the p probability is 0.1. So, lambda comes out to be 1. Here x we want to be 0 because we do not want to have any birth defect here. Okay. So, the p 0 1 will be e power minus lambda, lambda 0 0 factorial. So, that comes to e power minus 1, which is 0.367. So, that means there is a 36% probability that in a family of 10 people nobody is having the birth defect. Okay. So, we can also calculate one person having the birth defect. We use at least one person having the birth defect, then we can look at putting different numbers here based on what is the x we are looking at actually. Okay. Now, if you want to say probability of at least one person with the birth defect, that means the birth defect could be all 10 having birth defect, all 9 having birth defect, all 8, all 7, all 6, okay, having birth defect, 5 having birth defect, 4, 3, 2, 1. So, it will be like 1 minus nobody having birth defect. So, that is why we have 1 minus 0.367, so that is 0.633. That means probability of at least one person having birth defect in that family of 10 is 63%. So, here at least one person means, it means one could be having birth defect, 2 could be having 3 or 4 or 5. Okay. So, it is exactly 1 minus of nobody having the birth defect. Okay. Now, let us look at another interesting problem. This I took it from a website here. You were to scatter seeds over a large field from a plane. Imagine that you have divided the field into blocks of equal size. Okay. You have not dropped millions and trillions of seeds, but only small amount of seed. So, what is the probability that the seeds are independent of each other? Of course, one seed settling down is not going to affect the other seed's action. So, what is the probability that maybe at least one seed you get per plot, or what is the probability at least 2 seeds you get per plot? So, we can again use your Poisson distribution. Okay. So, as we can see, we can say at least one seed we can have about 36%, at least 2 seeds per plot you can have 40%. That means 2 seeds 0 or 1 seed it could be. So, like that we can calculate using the graphpad software. Okay. Now, let us look at another problem, and this is something related to genomics. Okay. So, the base composition of the thermococcus genome is about 0.21 is to 0.29 is to 0.29 is to 0.21, that is the mole ratio ACGT. Okay. So, the probability will be of A or C or G or T will be in this ratio actually. Okay. If the sequence were random, the probability that any given position in the genome is a SPEL site, that is ACTAGT would be, okay. So, that will be 0.21 of, because A is 0.21, C is 0.29, okay, and T is again 0.21, okay, and A is 0.21, G is 0.29, and T is 0.21. So, the probability that you have a genome sequence spell site ACTAGT will be all these actually, that is equal to 0.000164, that is one site per 6100 base pairs. Okay. Now, this genome is about 1,890,000 base pair. So, the expected number of SPL sites in a random sequence of this length and composition will be, so we have this 0.00164 multiplied by this, so we get the lambda is equal to 310. Okay. So, we can substitute that into our equation for less than 5. Okay. So, we want to look at less than 5, p equal to 0, 1, 2, 3, 4, 5. Okay. So, we are looking at x is equal to 0, lambda is equal to 310, x is equal to 1, lambda is equal to 310, x is equal to 2, lambda is equal to 310, x equal to 3, lambda is equal to 310, okay. X is equal to 4, lambda is equal to 310, x is equal to 5, lambda is equal to 310. So, if we substitute all this, we end up with such a very small number, okay, 5.7 10 power minus 125. But what is observed, okay, the observed number of sites is 5.13, okay, which is very big. So, obviously it is not a random event, because if it is a random event you should get this as a probability, but actually you are observing 5.13, that is at least 5 or fewer sites. Okay. Therefore, it is reasonable to reject the model that the nucleotide sequence of the thermocochlear cellular genome is random with respect to the sequence. So, it is not a randomly happening, because if it has to happen randomly, the probability of that is this, but actually you observe almost 5.13 or 5 or fewer sites, which is a large number. So, this sequence of ACTAGT, which is a SPL site happening, is not a random event. It is a very interesting problem. This, it was taken from this particular site, and so we can do similar studies on genome sequences, and when you see a particular sequence, you can see whether it is a random event using a Poisson distribution or it is not a random event. Okay. And so, once again to recap Poisson distribution, you have when n is very large, okay, so you have something called lambda here, which is the governing term. Lambda is given by n into p, p is the probability, n is the total number of events, it is given by e minus lambda, lambda x divided by x factorial. So, if we want to look at 0 event, then I put x is equal to 0 here, and if I want to look at 1 event, I will put 1 here, if I wanted 2, I put 2 here, 3, 3, and if I am looking at either absolute or I can even look at cumulative, that means probability of fewer than 4 events if I say, then I need to add all this. Okay. Now, we can use Poisson distribution also to find out confidence interval on the count. For example, if I am counting number of bacteria colonies in a plate, or if I am counting red blood corpuscles in the blood, these are all individual events. Obviously, if I take a different blood sample, I may get a different number. If I take a different blood sample from the same patient, I may get a different number. So, obviously there will be a range, it cannot be an absolute single value. So, that confidence interval is given by this term plus or minus t into square root of L. Okay. L is the average count, okay, but there is a confidence interval associated with this L, which is given by plus or minus t into square root of L, where t is 1.96 for 95% confidence interval and 2.58 for 99% confidence interval. Okay. This equation is very useful. Like I said, if I am counting the number of live bacterial cells in my plate, I get a number, say 10 power 20. So, what is the range, what is the confidence interval if I want to know? If I am looking at the red blood corpuscle of a volunteer, when I take a sample and count, I may get some number. When I take another sample, I may get another number. So like that, if I keep on doing it, I may get large set of numbers. So obviously there will be a confidence interval. So that is given by this particular term, t square root of L. L is the count, and t is given by 1.96 for a 95% confidence and 2.58 for a 99% confidence interval. Okay, let us look at some examples now that give you. In a counting chamber, I got 470 red blood cells counted under a microscope in a volume of 1 microliter. So what is the 95% confidence interval for the patient's true red blood cell count? So lambda is 470, so square root of 470 is 21.6, t is 1.96 for 95% confidence, so 470 plus or minus this. So the although we measure as 470 red blood cells, in reality if you want to mention it as a 95% confident, so it will vary between 427 and 538. So for a 95% I put this number as 1.96, whereas if it is 99% I put the number as 2.58. So the true value will be between 95% of the time it will be between 427 and 513. Okay. Now let us look at another plate. There are 100 agar plates containing antibiotics were streaked with 1 million bacteria each to determine the incidence of antibiotic mutants after incubation. In all, 58 mutant colonies were found. Okay, there were 58 mutant colonies. Calculate the probability of finding 0 or 1 mutant colony per plate. Okay, so obviously if I want to find 0, now I found 58 colonies in 100 plates. So my lambda will be equal to 0.58, that is the incident. Okay, if I want to see 0, then I put x as 0, so lambda raised to the power 0, 0 factorial, that is 56%. So if I want to see 1 mutant colony, obviously I will put e minus lambda, lambda raised to the power 1 factorial, so that gives you 32.5%. Okay, so you can see it is very useful. Poisson distribution, we can use it for calculating events based on a probability. These events are independent of each other, they are not related to each other. Okay, we can use Poisson distribution for getting a confidence interval for a count, like I showed you in example on red blood corpuscle, or if it is a bacterial colony I am counting. Okay, so Poisson distribution is very useful, and lambda is the only factor which I need to know. Here lambda is given by NP. Okay. Now I want to slightly switch gears and talk about something called population and sample. So population is something which is very big. Okay. For example, when I say there are 5 fatalities on the road in a metropolitan city, that means this data must have been collected over a very long time. Okay. So it is not that every day it will happen 5, but it is collected over a very long time, and that is called a population. Now if I am saying that the average height of Indians is 5 feet 5 inches, okay, so this data is collected over a very large data set, so that is called population. Okay. If you say the number of defects children born will be 1 in 1 million in India, then this data collected over a long period of time with large data set, and that we can call it population. Okay, okay, and that is generally denoted like capital N. Whereas I may take a small sample that is called a subset of this population. Because I cannot actually get all the population, but I can get a small sample. Suppose I am running a bolt factory, I take a few bolts and check their diameter, okay, and see whether it conforms with what I claim. Or if I take 10 people in Chennai and find their height, and I will try to see whether it matches with the Indian height average of 5 feet 5 inches. But that is a sample, that is a very small number, and even if I take 100 people, even if I take 1000 volunteers in Chennai and measure their heights, still I would call it a sample, it cannot be a population. So, there is always a population which is large, which is like an universe, you know, like the height of people in India, that is very big. Okay. Whereas when I take a small sample, that is denoted by small n, and in statistics, based on the results of sample, we try to predict what could be the population, whether the sample really falls into the population. I take 5 bolts and measure their diameter, I may get to say 20.1 mm, 19.9 mm, 20 mm. So, I will take an average. Now, I want to know whether this average conforms with the 20 mm bolt size which I have mentioned in my catalog. Okay. Is it really very close to 20 mm or is it very far away from 20 mm? So, when I take a sample, sample is always very small, and when I take an average of the sample, it will not be exactly 20 mm, the average may be 19.5 or 20.5. Now, this 20.5, is it very different from what I claim 20? Can I say they are same with 95% confidence, or can I say that they are same with 99% confidence? Okay, that is what statistics is all about. And so, the concept of population and the concept of sample play a very important role. So, sample is always very small, whereas population is very, very large. We can always collect samples, and based on the sample results, we try to say whether it comes from the same population or whether it is not coming from the same population. Okay. Okay, so when we have things like in continuous data, when I am measuring temperature 30.1, 30.2, 30.3 and so on, so I can calculate something called mean. Mean is nothing but average. Okay. So, everybody knows how to calculate mean. So, you add up all of them, divide it by the number of samples, okay, and then you get the mean. Normally for population mean we represent it as mu bar, okay, whereas for the sample mean we may represent it as x bar. Okay. Population mean we always represent it as mu here, whereas for sample mean we generally represent it as x bar. Like n is the population size, whereas small n is the sample size. Okay. Okay, so always sample means are represented by x bar, whereas population is always represented by, population mean is represented by mu here. Okay. Now, this sample mean is an estimate of the true population mean. Like I said, I take 10 bolts and then measure their diameter, take an average, that is x bar. Okay. Now, mu is what is the real population mean, which I say the bolts in my factory are 20 mm of size. Now, this x bar, how close is it with mu? Can I say that x bar is a good representation of mu, or is x bar very far away from mu, and so on, and that is what this statistical analysis is all about actually. Does x bar very close to mu, that I can say yes, x bar is a representation of the population, or x bar is not close to mu, it is not representation of this population. Now, when you say close or not so close, we use certain statistical terminologies like confidence limits, 95% confidence, 99% confidence and so on actually. So, we will talk about all these much more in detail as we go along. Now, median, what is median? Median is the middle point of the data set. Okay. So, if I have odd data sets, median will be exactly the middle point, whereas if I have the even data set, even means I have 20 numbers, okay, then obviously the median will lie between the two data points in the middle actually. Okay. Whereas if I have say 19, so I may have here both sides, okay, 9 and 9, and the middle point will be in the center, whereas if I have 20, I have 10 and 10, so obviously the median will be the average of the 10th and the 11th point, that is called median. So, median is the middle point, whereas mean is an average. Okay. Then there is something called mode. Mode is the value that appears most often in a data set. So, if you have say data set here like this, 23 is appearing many times. So, 23 is the mode of this data set. Now if the data set is like this, you have 3 and 6 appearing, right. So you have 2 modes, this is called a bimodal distribution, whereas this is a monomodal. So we have 3 terms, the mean, median, mode. Mean is the average, median is the central point, mode is the value that appears most often in a set of data. So we will be using these in our statistical calculations as we go along actually. Thank you very much for your time.